then I'll now take over to start talking in a bit more detail about the water-stable isotopes, what they are, and how they can be useful for water resources management applications. And the applications are many. As Daniele already explained, in Watson we focus on the entirety of the Earth's skin from the atmosphere to the bottom of the ground water. And water affects almost all processes in this critical zone, as we refer to that environment. And this includes interactions between the atmosphere, living beings, soil, and rock. And many environmental and water management challenges that are being faced today, they are dependent on water sources, the pathways this water takes, and also the age of water. So how long does it take for water to be in different compartments and move between them? And understanding how much water is available when and how clean is this water, that's really key for addressing water resources in agriculture, but also predicting and mitigating the effects of climate change, preventing water shortages during drought, but or understanding and addressing floods. So if we focus briefly again on the three main themes of the Watson action for water resources management, questions that water managers may have and where isotopes could potentially help. They include those around water use, land use, planning, forestry, agriculture. For example, our first theme focuses on the flow of water from the surface through the soil and to the groundwater. And this relates to questions of recharge of groundwater systems and water availability. Our second theme focuses on the flow of water absorbed by plants and from the soil given back to the atmosphere. And this has important questions around plant water requirements and water uptake in agriculture and forestry, for example. And the last theme that focuses on the paths followed by water to travel from the atmosphere to the streams. This has many important applications, including, for example, determining pollution travel pathways and travel times. But what then are isotopes and how can they help? I'm sure you're all aware that a water molecule consists of oxygen and hydrogen, and two hydrogen elements. That's indicated by the H2O. And that's represented here in the schematic on the left. And this is where I'm going to make it a little bit more complicated and explain that each of these elements consists of a number of protons, neutrons, and electrons. And that's indicated here in the schematic on the right. And we can see that typically an oxygen element, that's the bigger circle within the molecule. This has 8 protons in red and 8 neutrons in gray. And the hydrogen element typically has 1 proton. And the number of protons and neutrons, they make up the atomic mass or weight. And for oxygen, this is 16, and for hydrogen, this is 1. But these are the most standard versions, because in reality, other isotopes do exist. So what isotopes are forms of the same element that contain an equal number of protons, but different numbers of neutrons. And the key implication is that they have differences in their atomic mass, but not in the chemical properties. So this means that for oxygen, we can have oxygen 16, 17, and 18 as stable forms, so they don't decay. And for hydrogen, this is H1 and H2. If I've lost you here, all you need to remember is that isotopes of water have different weights. And because some elements have more neutrons, and that means that this isotope which is heavier, basically. And the most common forms are the lighter isotopes. So they are indicated here in the light blue in the schematic, and the heavier isotope is indicated in darker blue. And each sample of water has a combination of the lighter and heavier water isotopes. And this ratio between lighter and heavier isotopes, that's the result of a lot of different hydrological processes. And what it does is it gives the water sample a unique fingerprint. And we can use this to trace through the water particle through the critical zone to understand water sources, water pathways, and the ages of water. So some of the processes that determine the ratio of the heavier and lighter isotopes involve rainfall, and mostly relatively more of the heavier isotopes fall earlier in a rainfall event, and reversely during evaporation, the lighter isotopes go back into the atmosphere first. And because of these processes, rainfall is highly variable in the isotope ratios, both in space and in time. And we use that to track the water through the system that you can see here on the top right. And because rainfall is variable and there's various mixing of old and new water, there's so much variation in the isotope ratios in different parts of the water system. So we can use these isotope ratios then to trace the water, so to understand the water sources and trace water along their pathways that it takes and how long that it takes. And I should make a quick note here that we use isotopes to understand the sources, pathways, and age of water, but we often do this in combination with other hydrological measurements, such as the measurements of the amount of water that is involved, because that's of course part of the question too. So in a recent meeting of Watson members, we collected information on where and how stable isotopes have previously been applied to water resources management challenges. And I've just put a few on the screen here, and they include the determination of research areas, which were then being managed for land use. Separating out sources of tap water. Is this fairly recent surface water or older groundwater that is coming out of the tap? Understanding and monitoring the consistency of sources, or even checking the bottled water origins. And there are also many applications around determination of pollution sources, estimation of recovery times from pollutions, and other water management challenges, such as leakage of surface waters.